Hello everyone, I present my work about DETRs with hybrid matching. Since the success of DETR on object detection tasks, DETR-based approaches have achieved significant progress on various fundamental vision recognition tasks. A key design for DETR is one-to-one set matching, which helps DETR to establish its end-to-end capacity so that object detection does not require a handcraft NMS to remove duplicated detections. But the one-to-one set matching also significantly reduces the training efficiency because only a small set of queries can be assigned to the ground truth. To overcome the drawbacks and unleash the benefits of exploring more positive queries, we present a very simple yet effective hybrid matching scheme, which introduces an additional one-to-many matching branch that assigns multiple queries to its passive samples. We find that this simple approach can improve the training efficiency as well as the model performance. We name the hybrid matching approach as DETR and verify its effectiveness using a variety of vision tasks as well as different model sizes ranging from resonant, semi-tiny to semi-large. Our hybrid matching scheme can improve the DETR model performance across 5 challenging vision tasks, include 2D object detection, 2D panoptic segmentation, 2D path estimation, 3D object detection, and multi-object tracking, and beats the state-of-art approaches in some tasks. Let's review the general pipeline of DETR first. Given an input image, DETR first applies the backbone and the transformer encoder to extract a sequential of enhanced pixel embeddings. Second, DETR sends the enhanced pixel embeddings and a default group of object query embeddings into the transformer decoder. Third, DETR applies the task-specific prediction heads on the updated object query embeddings after each transformer decoder layer to generate a set of predictions independently. Last, DETR performs one-to-one matching between the predictions and the ground truth bounding box and labels. In the one-to-one matching, DETR associates its ground truth with the prediction that has the minimum matching cost and applies the corresponding supervision accordingly. The one-to-one matching avoids a handcraft NMS to remove duplicated detections, but it also slows down the training process because only one query is assigned to its ground truth. According to our observation, the form of DETR normally only selects less than 13 queries from a pool of 300 queries. That's because nearly 99% of the COCO images consist of less than 13 bounding box annotations, while the remaining more than 2,017 queries will be assigned as non-object and are supervised with only classification loss, thus suffering from very limited localization supervision. This problem could be solved by changing the one-to-one matching into one-to-many matching. You can see that in the one-to-many matching, the ground truth is repeated for certain times so that multiple predictions will be assigned as positive samples for each ground truth box, so queries can get more supervision. But using one-to-many matching for training will make the model eventually produce duplicated predictions in the evaluation process, and the time-consuming NMS has to be taken to remove them. So what we need is to combine the advantages of the one-to-one matching scheme with those of the one-to-many matching scheme, where the one-to-one matching is necessary for removing NMS, and the one-to-many matching erases the number of queries that are matched with the ground truth for higher training efficiency. That's why we introduce hybrid matching. We introduced 3 hybrid matching schemes for DETR, that is hybrid branch, the hybrid epochs, and the hybrid layer. For hybrid branch scheme, we introduce an additional one-to-many matching branch when training, where we simply repeat the ground truth for k times and get an augmented target. We also perform the matching between the predictions and the augmented ground truth pair over every layer and compute the same losses used in the original one-to-one matching branch. To accelerate the training speed and process both 2 branches in parallel, we further apply a masked multi-head self-attention to avoid their interactions. Therefore, we do not observe significant extra training costs in experience. In the hybrid epoch scheme, we only maintain a single group of queries, where we apply both one-to-one matching and one-to-many matching on the predictions during different training epochs. During the first 13 epochs, we perform one-to-many matching to accelerate the training progress. Then we change the one-to-many matching to one-to-one matching for the remaining training epochs to avoid the duplicated predictions. In the hybrid layer scheme, we also maintain a single group of queries, just like the hybrid epoch scheme. Instead of performing different matching strategies across different training epochs, we apply one-to-many matching or the prediction output by the first certain transformer decoder layers, and one-to-one matching or the prediction output by the remaining transformer decoder layer. From the left precision recall curves, we can see that our approach consistently improves the recall of the baseline under two different IOU thresholds. And from the right table, we can see that hybrid matching approaches consistently outperform the baseline under different training epochs, and the hybrid branch scheme is the best choice if we consider the trade-off of training time, inference G-flops, and FPS, and accuracy. Therefore, we choose the hybrid branch scheme by default if not specified in the following ablation experiments. Result on the COCO object detection validation set shows our H deformal DETR achieves consistent gains over the baseline or with backbones of different scales. Besides, we report the compression result on average object detection in the right table. Our approach also achieves consistent gain over the baseline deformable DETR across the various backbones, like the R15 and spin large. Recent DETR-based approach, the Peter V2, to verify the generalization ability of our approach for 3D detection based on multi-view image. This table summarizes the detailed comparison results. We can see that our the Peter V2 significantly improves the NDS score of baseline Peter V2 on new size validation set. That's showing that our hybrid matching improves the localization accuracy of 3D object detection predictions. We extend our hybrid matching strategy to the very recent Peter and summarize the detailed results in this table. We can see that our approach achieves consistent gains over the baseline on the multi-person post estimation. We apply our hybrid matching scheme to a powerful multi-object tracking approach, the TraceTrack. This table summarizes the detailed comparison results. We find the results on MOT7 suffer from relatively large variance. Thus, we report the mean performance with 3 ROAS accordingly. Our approach also shows strong potential on the multi-object tracking tasks, and our TraceTrack improve the MOTA score of the TraceTrack largely on MOT17 validation set, where we also observe that the gains are related to much lower false negative rates. This table reports the system-level comparison to some state-of-the-art methods that use single-score evaluation on COCO validation and choose backbones of similar capacity with spin large. By introducing additional enhancement technologies, our H deformable DETR achieves the best on COCO validation set with surpassing the very recent Dino DETR.